In our Do Now today, we're going to go over our rules again for our negative exponents. We're going to simplify, so just want to go over what that working definition is for us with simplify. Okay. So that's going to be no exponents with number bases, meaning like a 2 to the 4th, that's not simplified. No parentheses, so we don't want something like -3 squared, right? Those parentheses wouldn't be simplified. And no negative or 0 exponents. So let's do all that as we work on our do now. So number 1, we have 6b to the -2nd power. I want to make sure I'm identifying what is the base of that negative exponent. It's b, just b. 6 is that coefficient. There's a multiplication in there. So only the b and its exponent of -2 are going to move to the denominator. So this becomes 6 over b squared. And there we are, fully simplified. On number 2, there's a couple of things I want to notice. One, that the 2 and 6 have common factors that can be reduced. 2 goes into 2 once, 2 goes into 6 3 times, just like we're reducing a fraction. Then I want to notice the negative exponent in the denominator. The base of that negative exponent is just x. Only x is going to move. Everything else is going to stay the same. When we have variables, when we have numbers where we don't see an exponent, there's really an exponent of +1. So all of those are fine staying where they are. So as we go and move it up, remember I reduced up here, so we have 1x, and then we're going to have x squared over 3y. Now this isn't fully simplified. That x and x squared, well, we know what that is. X times x squared. If I'm doubting, I like the phrase, when in doubt, expand it out, and I look for what's going on here. X times x squared is x times x. Now I see, oh, x times x, that's just x to the 3rd. Okay? And some of us might not have needed that expanding. We might have been able to just go right to x to the 3rd over 3y. Okay. Our third rule of our negative exponents is, what do we do when we have a fractional base being raised to a negative power? Well, we flip our fraction and make the exponent positive, right? Exponent with a number base can't have that. So let's see what's going on there. That's 5 over 4 times 5 over 4 times 5 over 4. So that's going to be 125 over 64. And there we go. All done. Okay. One example I wanted us to go over was just something that I see as a common error for students. So if we have the directions of simplify, sometimes we could have something like this, where we have negative x squared. Now a student's natural reaction is to say, hey, oh, combine the double sign. No, you cannot combine the double sign. That negative is like a coefficient. That's really saying -1 times -x squared, right? Order of operations, we must do exponents first before we multiply. That -x is the base. -1 times -x times -x. -x times -x is +x squared. -1 times x squared, -x squared. Okay, so you can't just combine that double sign. We really have to take those steps to simplify and expand and evaluate what's going on there. Okay, so we're going to go to page 8 in our booklet and look at our exponents with similar. On page 8, our exponents with similar bases. We're going to expand our expressions and then simplify them and look to see if there's any sort of shortcuts that we can come up with that we can use, which will be convenient for our longer expressions. So we've got 3 squared times 3 to the 3rd, so we'll expand those out. So we've got our 3 squared is 3 times 3, and then we're going to multiply our 3 times 3 times 3. Now I can see that that's really 3 times itself 5 times. I just wanted to show how we kind of group that together. Obviously that's not simplified, and I don't have in the top of my head what 3 to the 5th is, so I'm going to use my calculator. It's 243, and that would be our answer, fully simplified. With our next expression, a times a to the 5th, I want us to think about, well, what's the exponent on that first a? It's just a 1. Write that in with me. That's going to be important as we go to make a connection later on. So we've got that first a, and then times our 5 a's times itself. We should be able to see we're actually multiplying 6 a's together. So it would be a to the 6th, fully simplified. Hopefully we're starting to notice a pattern now. Negative 4 to the 3rd times negative 4 to the 4th. It's in parentheses, so both bases are negative 4. They're the same base. So if we expand that, that's negative 4 times negative 4 times negative 4 times now our negative 4 to the 4th. And I'm just going to show what it is, that's really negative 4 in parentheses to the 7th power. If we think about it, negative 4 times negative 4 times negative 4 times negative 4 times negative 4. We're multiplying a negative an odd number of times. I know it's going to be negative, and I don't expect you to be able to do this by hand, so I'll use my calculator. 4 to the 7th is 16,384. So negative 16,384. Now, here, 2y to the 3rd times 4y to the 6th. I want to make sure I'm realizing that the 2 and the 4 are coefficients. They're not a part of the base. And we're going to expand this more than once. Okay, so let's kind of look at what we have. We have 2 times y times y times y times 4 times y times y times y times y times y times y. Now this is where our commutative property comes in really handy. We can reorder putting our coefficients next to each other and then all of those y's next to each other. So that was y to the 3rd and then times y to the 6th. And if we look at that, 2 times 4, we know how to do that. That's 8. And then that's 1, 2, 3, 4, 5, 6, 7, 8, 9 y's being multiplied. That's going to be 8y to the 9th. Okay, so we want to look for a pattern here, sort of coming up with a shortcut. So I'll ask you, what do you notice happens when we have expressions with the same base and they're being multiplied? Right. So we want to notice that when multiplying exponential expressions with the same base, we are going to, what do we do with our coefficients? We multiplied the coefficients. We added the exponents, right? 2 plus 3 is 5, 1 plus 5 is 6, 3 plus 4 is 7, 3 plus 6 is 9. So we add the exponents, and then what do we do with the base? Still 3, still a, still negative 4, still y. We keep the base the same. So just to review, if we have coefficients, we're multiplying those coefficients, we're keeping the base the same, and adding the exponents. Okay, that's when we are multiplying exponents with same bases. So down here we've got algebra a to the n power times a to the n power. To show that algebraically, keep the base the same, and add your exponents, a to the n plus n power. Okay. Now we'll go on to division. Okay. So first thing I want to do when we have these expressions, it's going to be really convenient to see them structured like fractions. So I'll take 3 to the 4th divided by 3 squared and rewrite it that way. And then we're going to expand. So our numerator, 3 times 3 times 3 times 3 over 3 times 3. Now we want to look, what's the same on the top and the bottom? We can cancel out the 2 3's on the bottom with the 2 3's on top. That leaves us with 3 times 3 in the numerator over 1, or 3 squared, which is 9. Right, so we have the 2 3's up top because that's where our leftovers were, and then just that 1 on the bottom. Okay. Let's try it again with our next expression. Negative a to the 4th divided by negative a. Remember, that's our little exponent of 1. I'm just going to restructure it as a fraction so we can see it. Okay, and that was in parentheses to emphasize the base of negative a. So we'll expand the top. Now we have just one of the negative a's that can cancel. Now to see a connection, I'm just going to rewrite it as an exponent, right? That would just be negative a to the third power over 1. We know that's not simplified because it's parentheses, so I'm going to look back here. Negative a times negative a would be positive a squared times negative a would be negative a to the third power. That's our simplified answer. Help us make a connection, simplified answer. Okay. Now we have a squared over a to the fifth, right? So that's a squared in the numerator, a to the fifth in the denominator. Right, so we've got a times a in the numerator and a times a times a times a times a in the denominator. The two a's in the numerator cancel with two a's in the denominator, leaving those three a's in the denominator and a to the third in the denominator. What's in the numerator? 1. So we have 1 over a to the third. Now, just for conversation, to help us make a connection, remember, 1 over a to the third, that's the same as a to the negative third power. Just write that down. Maybe it'll help us see a connection later on. But our simplified answer, 1 over a to the third. That's the correct simplified answer. Okay. Now, the next one here, really big. Really long. We've got a fraction of x with exponents times a fraction with exponents. So let's just kind of write it all out here. Now remember, fractions, we multiply top times top, bottom times bottom. So we can make one big long numerator here. So that's going to be 2 times a times c times a times a times a. And then the denominator, 5 times a times a times a times a times a times a times a, there's our 7 a's, times 4 times c times c. Now from here, I would suggest reorganizing, so putting all the a's together up top, so that should be 5 a's up top, times 1c, over in the denominator, 5 times 4 is 20, times 7 a's, 1, 2, 3, 4, 5, 6, 7 times 2 c's. I gotta extend my numerator. Okay. Now we want to look to reduce. So I notice 2 goes into 2 once, 2 goes into 20 10 times. Now 5 a's on top can cancel with 5 of the 7 a's on the bottom. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1c and 1c. Okay. Now we'll look to rewrite what we have. So in the numerator, just 1. In the denominator, 10 a squared c. That was a big one. 1 over 10 a squared c. Okay. Now looking for a connection, my suggestion is let's look to the top 2 examples for our connection. I think that's where we're going to see it the best. How do we go from 3 to the 4th over 3 squared to 3 squared? How do we go from negative a to the 4th divided by negative a to the 1st to negative a to the 3rd? So what we should be seeing there is that we're keeping the base and subtracting our exponents. And that even works here with a squared over a to the 5th. 2 minus 5 is negative 3. Oh, a to the negative 3rd? That's our answer. We just have to simplify and rewrite it with a positive exponent. Now, yes, the rule does work here. I don't use the rule as much saying, oh, let me subtract. What I do here is I think about more of canceling. That I see, oh, I have 5 a's up top. That's going to cancel with 5 a's in the bottom, and I'm going to have 2 a's left over on the bottom. So we get a squared. One C up top is going to cancel with one of the C's on the bottom, and I'll be left with one C on the bottom. And we'll do another example like that together. So here we go. When dividing exponential expressions with similar bases, we're going to divide, or we can say reduce the coefficients, subtract the exponents, and keep the base the same. And then down here we have our algebraic example. AM divided by A to the N. Well, that's going to be A to the M minus N power. Okay. So now is where you want to go and use your separate sheet of paper, and we'll do another example together. First example I wanted us to do together is an example where we're going to use our multiplication rule, multiply our coefficients, keep our bases, and add our exponents. And I just wanted to show an example where expanding out really wouldn't work here. For most of our examples, yes, if you want to, you can expand out, but I am not going to write y 18 times and then another 10 times. I'm just not doing it. I got better things to do. So here we're going to use our rule, right? I see same bases. 5 times 7 is 35. Now I go to my x's. Well, if I have 12 x's, and I'm multiplying in another 4 x's, that's going to be 16 x's being multiplied together. So x to the 16th. Y to the 18th times y to the 10th. Well, I have 18 y's being multiplied, another 10 y's. That's going to be y to the 28th. And we can see that's a lot faster than expanding it and writing it all down. I also wanted to do a division example. As I talk through this, you'll notice I'm not going to be doing the subtracting. That's not really how I'm thinking about it with that subtracting rule, where I'm saying, oh, 3 minus 1 is 2, because then I find students get confused, like, where is the y squared? I like to think of it more as canceling. So I know I'm going to have a 4 in the denominator because there's nothing with it to cancel. And we have x squared up top and x to the 9. So I kind of just visualize, okay, that means 2x is being multiplied up top, 9x is being multiplied on the bottom, which means I can cancel out 2. So we're going to have 7x's left over. Where are they going to be left over? On the bottom. So that x to the 7th is going to be on the bottom. Y to the 3rd up top, y to the 1st on the bottom. I can cancel 1y. There's going to be 2 left over. Where are they going to be? On the top. And there we go. That's it. You guys are working on pages 9 and 10 in your booklet today on classwork. You'll notice the directions are expand and simplify. I want you have to simplify, but really only expand if you want. If that's the strategy you're using, then you should expand. If you want to use more of our rules and do more of the visualizing like I did in the examples, just go right to the simplifying though. But if as you're checking your work, you're checking the answer key, you're getting something wrong, I'm always going to go back to that phrase I've been saying, that when in doubt, expand it out. Okay, so if you're having trouble, get a piece of scrap paper, write it all out so you can see it. Today's math jokes for Matthew folks. Life without geometry is pointless. Get it? Geometry, pointless? All right, have a great day.